in the previous videos, we looked at the line y equals x. So y equals x will look something like this: the diagonal line going through the origin. So this is a graph of y equals x. And then we looked at y equals x squared. Well, y equals x squared looks something like this. Okay, it looks like a U shape and it's symmetrical. And then we looked at y equals x to the power 3. Well, this looks something like this. Something like this. And what I want to point out in this video is that you may think that this bit here is very much similar to this bit here, but it's not really, because this is a lot steeper. Hang on, let me show you why. The point of this video here is to show you that if you look at this bit here, a lot of people think that this is pretty much the same as this, but the two are very different. And look why that is. Okay, let's look at x. Let's look at y equals x squared. Now y equals x squared will look something like this. 1 times 1 would be 1. 2 times 2 will be 4. So it looks like this. And 3 times 3 would be 9. Okay, and 4 times 4 would be 16. So somewhere up here. Okay, so the graph of y equals x, I'm going to try my best. It's really hard to draw a curve on this pad. Okay, wait, something like this. Okay, and it is symmetrical. So hang on, let me think. So 4 will be somewhere here. Okay, so this is the line of y equals x squared. Now, if you look at y equals x to the power 3, well, yes, it still goes through the origin. When x equals 1, it's 1 times 1 times 1. So that's still at the same point here. But when you look at 2, now so when you look at 2, with x squared is 2 times 2. With x to the power 3 is 2 times 2 times 2. So x to the power 3 would be 8. So this one here would be 8. And now when you look at 3 over on the x squared side is just 3 times 3. But over here, 3 times 3 times 3, it jumps up massively. So this here would be 27. This here would be 27. So here, this is when x equals 3. With x squared, it's here. Now when x to the power 3, it would jump all the way up here. Hang on, it would jump off the scale. So it would be 27. So it's probably all the way up here somewhere. So look at this here. So hang on, if you look at x squared, it climbs like this slowly. Okay, but when you have x to the power 3, it jumps up massively. So my point is, if you look at this here, this is y equals x squared. This is y equals x to the power 3. When you sketch it without the scales, people would sketch it like this. And when they sketch x to the power 3, they would sketch it like this. Now, without the scale, this bit here looks so much similar to this bit here. So people think it's the same, but it's not, because hang on, if you try and do this here, if we plot the two graphs on the same two lines on the same graph, it will look like this. X squared will look something like this. Hang on. And then x to the power 3, y equals x to the power 3, it climbs massively. So it's something like this, and then it climbs a lot faster than the x squared. Hang on, let me do it again. So it climbs something like, it climbs even steeper than that. So something like that. Okay, if you draw the two lines on the same scale. So my point is that x squared will look something like this. Now x to the power 3, it climbs so much steeper. So if you can just bear in mind that hang on. Let me try and illustrate it by drawing a better line here. So here, this is y equals x squared. And when you have x to the power 3, it climbs a lot steeper. Well, I think you get the idea. Hopefully, you get the idea. So just remember that if you just look at this quadrant here and this quadrant here, the two are not the same. This one here is a lot steeper than the x squared. Okay.